Hidden inside a distant galaxy known as LRG 3757 lies one of the heaviest black holes ever discovered, weighing billions of times more than our Sun. How can such an immense object even exist? And what does it mean for the universe around it? Stay with us as we uncover this cosmic giant. If you enjoy the journey, please like, subscribe, and share. And tell us in the comments, do you think there could be black holes even bigger than this? Thank you for watching. Now, let's begin. In the distant fabric of the universe, vast structures of matter are arranged like threads woven into a cosmic web. Galaxies are not scattered randomly, but lie along filaments of dark matter that span hundreds of millions of light years. These filaments connect to each other, forming nodes where gravity has pulled together countless galaxies, clusters, and immense halos of unseen material. Between them stretch enormous voids, regions that appear almost empty when compared to the glowing chains of matter. This pattern emerged gradually over billions of years as gravity amplified small variations that once rippled through a hot, nearly uniform early cosmos. Today, telescopes trace these patterns across the sky, showing that galaxies are the bright signposts of deeper structures that remain hidden. In such a web, matter is not only luminous but also invisible, with the unseen component outweighing the visible. Dark matter, which does not emit or absorb light, supplies the underlying scaffolding on which galaxies are built. Its gravity controls the motions of stars and galaxies alike, and its presence is revealed only by its effect on ordinary matter. Cosmological surveys show that dark matter outweighs visible matter by more than 5 to 1, and its distribution determines the layout of the cosmic landscape. Observations from satellites like the Planck mission reveal that this architecture took shape soon after the Big Bang, with the early distribution of matter setting the stage for all subsequent evolution. Clusters of galaxies form at the densest nodes of this cosmic web. They are immense concentrations of matter, each containing thousands of galaxies bound by gravity with masses equivalent to quadrillions of suns. Between their galaxies lies hot gas that glows in X-rays and enormous envelopes of dark matter that cannot be seen directly. These clusters are among the most massive structures in the universe, and their gravitational influence extends for millions of light years in every direction. Within clusters, galaxies experience tidal forces, collisions, and merges shaping their forms, and sometimes fueling activity in their centers. The cluster environment is harsh, stripping galaxies of their gas and leaving many of them as smooth elliptical systems dominated by old stars. The density of such places makes them laboratories for extreme astrophysical processes, from shock waves in intracluster gas to bursts of star formation triggered by encounters. Among these structures, there are smaller groupings as well. Not all galaxies reside in such massive clusters. Many exist in loose groups containing only a few members. These groups, while less massive than clusters, also reflect the cosmic web's underlying framework. They serve as environments where galaxies can still interact, merge, and evolve, but on less extreme scales. It is in such regions that gravitational lensing sometimes reveals itself most strikingly. When a massive galaxy lies along the line of sight to a more distant one, its gravity bends and magnifies the light of the background source. This bending is not due to a physical obstruction, but to the curvature of space-time itself, a direct consequence of general relativity. The result is that light follows curved paths, producing arcs, rings, and multiple images that would not otherwise exist. These distorted shapes allow astronomers to measure the mass of the intervening galaxy with remarkable precision, including the contribution from dark matter that would otherwise remain invisible. Such lensing events are rare and striking. They appear as curved arcs of light surrounding a central galaxy, evidence of gravity's profound effect on the path of photons traveling across billions of years. The precise configuration depends on the alignment between observer lens and background source, as well as the mass distribution of the lensing object. When alignment is nearly perfect, the background light can form nearly complete circles known as Einstein rings. Even when not fully circular, the arcs they create can be large and bright enough to be studied in detail. These phenomena not only reveal the total mass of the lensing galaxy, but also magnify distant galaxies that would otherwise be too faint to study. Through them, astronomers peer deeper into cosmic history, viewing galaxies in their early stages of formation. Within this grand context, the system known as LRG 3757 resides. It lies as one participant in the intricate cosmic tapestry distinguished by its extraordinary gravitational influence. It is not alone in its region of space, but connected to the web of matter that stretches across the cosmos. The arcs of light around it are not random shapes, but the visible trace of curved spacetime are a direct indicator of the immense mass it contains. Though only one among many galaxies, it stands out because of the scale of the bending it produces. From Earth, the distorted light is captured by instruments capable of detecting the faint glow of distant sources, allowing astronomers to reconstruct the mass distribution with clarity at the scale of billions of light-years. Distances blur human intuition. Light that arrives today from the lensed background galaxies began its journey when the universe was much younger, crossing expanding space before being diverted by the gravity of the intervening system. This time depth means that what is seen is a combination of multiple epochs. The lensing galaxy as it was billions of years ago, and the background galaxy as it appeared even earlier. Lensing in this sense is both a window into the distribution of mass and a time machine reaching back into early cosmic eras. In the case of this particular system, the arcs form a near-complete ring often referred to as a cosmic horseshoe, an image that has captured attention not for symbolism but for its rarity. Few alignments in the observable sky produce such striking and symmetric patterns. The study of such a lens requires careful observation. Surveys that chart wide areas of the sky look for candidates, and once an unusual arc is spotted, follow up with higher resolution imaging refineses the picture. The arcs are modeled using equations of general relativity, allowing astronomers to map the distribution of matter in the lensing galaxy. This method is particularly valuable because it does not rely on light emitted by the galaxy itself. Instead, it depends on the way mass warps the paths of photons. In this way, lensing becomes one of the most direct tools for measuring the total mass of galaxies, including both visible and invisible components. When the light paths are mapped, the extent of the bending reveals the true scale of the galaxy's gravitational field. For ordinary galaxies, arcs are faint and small. For massive ellipticals like LRG 3757, the arcs extend broadly, indicating not just a concentration of stars, but an underlying reservoir of dark matter, and in the center, something far denser. Still, the distribution can be reconstructed as a profile of increasing density toward the core. Each layer of mass contributes to the overall curvature of space, guiding the background light into its observed shapes. As a result, even without directly seeing the innermost engine, astronomers can infer its presence from the way space itself is curved around it. At the scale of cosmology, this galaxy is one among billions. Yet the depth of its gravitational imprint makes it stand out in the survey data. The horseshoe-shaped arc is not just visually striking, but scientifically significant. It shows that gravity here is exceptionally strong, requiring an immense concentration of matter. In the background, faint galaxies serve as light sources. But the true story is the foreground system that bends them. From this starting point, the exploration of its structure and the extraordinary black hole at its core begins layer by layer, always moving inward. From the broadest context toward the central heart of gravity across the larger neighborhoods of the universe, galaxies do not exist in isolation, but as members of groups and clusters. These associations range in scale from small gatherings of only a few galaxies to vast collections, numbering in the thousands. The clustering of galaxies arises from the distribution of dark matter, whose gravitational field gathers luminous matter into the nodes of the cosmic web. As a result, the universe presents an intricate hierarchy. Filaments feed material into groups. Groups assemble into clusters and clusters, sometimes merge to form even larger superclusters. In these environments, galaxies are subjected to complex interactions that shape their structure and fate. Gas is stripped from them as they move through hot intracluster plasma, while their stellar halos are distorted by gravitational encounters. Over cosmic time, many galaxies lose their spiral arms and settle into more featureless ellipses, their stars orbiting in random directions instead of the orderly rotation of a disk. In the regions where matter collects most densely, the gravitational potential wells are deep enough to trap gas at temperatures of tens of millions of degrees Kelvin. Such hot plasma fills the spaces between galaxies, emitting X-rays detectable by space-based observatories. These observations show that a large fraction of the baryonic matter in clusters is not in stars, but in diffuse gas. The gravitational field of dark matter confines this gas, preventing it from escaping despite its high temperature. The combined presence of galaxies' plasma and dark matter creates some of the largest bound structures in the universe. The scale of these systems is measured not in millions, but in tens of millions of light-years across, and their total mass can exceed 1,000,000 billion times the mass of the Sun. The galaxies within them are bound together in a gravitational dance, their paths influenced by the combined mass of all members. In such a setting, the lensing system known as LRG 3757 has its place. Its arcs and distortions reveal that it lies within an environment where mass is unusually concentrated. The host galaxy itself dominates its local surroundings, but the context of its neighborhood adds to the total field. Galaxies that lie nearby contribute to the bending of light, even if only slightly. Astronomers account for this by modeling not just the mass of the central galaxy, but also the distribution of matter in its environment. This makes gravitational lensing both a challenge and an opportunity. While complex to disentangle, it allows for detailed mapping of mass over a wide area. The result is a layered view in which the central system emerges as a dominant peak atop a broader landscape of matter. The environment of massive galaxies in groups or clusters has further consequences. Their interactions strip them of cold gas, leaving them unable to form many new stars. Their colors shift toward the red, reflecting populations of older, cooler stars that dominate their light. Over billions of years, repeated encounters smooth their structures into the rounded forms typical of elliptical galaxies. Many such systems harbor central black holes whose masses correlate with the properties of their host galaxies, suggesting a shared evolutionary history. The largest galaxies, often found at the centers of clusters, contain the most massive black holes. This pattern indicates that galaxy growth through mergers and black hole growth through accretion are connected processes, each feeding into the other over time. Clusters are also dynamic environments where subclusters fall together and merge, creating shocks in the intracluster gas and stirring up turbulence. These collisions can last for hundreds of millions of years, during which galaxies are thrown into new orbits and gases redistributed. The evidence of these processes can be seen in radio observations that detect extended relics and halos, signatures of particles accelerated in cluster-scale shocks. These environments are extreme laboratories for the study of gravity, gas dynamics, and particle physics. For the galaxies within them, the long-term result is transformation, and sometimes destruction as smaller galaxies are absorbed into larger ones. Measurements of the motions of galaxies within clusters provide direct evidence for the presence of dark matter. The speeds at which galaxies move are far too high to be explained by the gravity of visible matter alone. Similarly, the temperature of the intracluster gas requires additional mass to confine it. Gravitational lensing offers a third line of evidence independent of both. Together, these methods converge on the conclusion that clusters are overwhelmingly dominated by dark matter. This invisible component is not a minor addition, but the main contributor to their mass budget. In this sense, visible galaxies are traces floating in a much larger and heavier sea of unseen matter. When examining the neighborhood of the lensing system, astronomers consider both the large-scale environment and the local context. Isolated galaxies can act as lenses, but those embedded in denser regions produce more complex patterns. The lensing arcs of LRG 3757 appear symmetric enough to suggest that the mass distribution is dominated by the central galaxy itself, rather than a complex interplay of many nearby ones. Even so, the broader neighborhood cannot be ignored. It establishes the stage upon which the central galaxy has grown to its present size, accumulating mass through the gradual merger of smaller systems. Each collision would have brought not only stars, but also central black holes, which eventually sank to the core and merged into a single larger one. Over billions of years, such processes created the massive elliptical galaxy visible today. In cosmological terms, these structures are not static. Clusters continue to grow as material flows along filaments of the cosmic web. New galaxies fall inward, adding their mass to the central system. The universe itself expands, stretching the distances between superclusters, but gravity holds these dense knots together. Within them, time seems to slow relative to the overall expansion as their internal gravity dominates over the cosmological background. This means that the environments where the largest black holes are found are also those most resistant to the universe's stretching fabric. They are anchored places massive enough to maintain their coherence even as the cosmos at large grows ever more diffuse. The larger neighborhood of this particular system can thus be seen as both cradle and container. It supplied the raw material for the galaxy's assembly and continues to hold it in a gravitational grip. The arcs of light serve as proof of the density of the region, while the stellar population of the host speaks to the long evolutionary path it has followed, step by step from the broadest web of filaments to the densest knots of mass. The stage is set for the remarkable concentration of matter found at the core. From here, the journey continues inward, narrowing from neighborhood scales to the distinctive lensing features that first drew attention to the system. The discovery of unusual systems in the sky often begins with surveys that scan wide areas in search of faint structures. These surveys, conducted with ground-based and space-based instruments, create catalogs of galaxies by capturing their light across multiple wavelengths. By analyzing these catalogs, astronomers identify candidates that stand out for their brightness, shape, or unusual alignment with background objects. One such system revealed itself through the peculiar bending of light, its image differing from the typical forms of elliptical galaxies. The arcs encircling it marked it immediately as a gravitational lens. What distinguished it further was the symmetry and brightness of the arc, suggesting not only a significant mass, but also a rare alignment with a distant background source. Such alignments are not common for the positions of foreground galaxies. Background galaxies and Earth-based observers must line up precisely. When they do, the result is an optical signature that cannot be mistaken for anything else. This is how the system known as LRG 3757 entered scientific awareness. Its detection came through a survey designed not for beauty, but for completeness, seeking to map galaxies over wide stretches of the sky. The acronym ALARI refers to luminous red galaxies, a category of galaxies used in large-scale structure studies because of their brightness and uniform properties. Their red color indicates old stellar populations, and their luminosity makes them visible across great distances. By including such galaxies and catalogs, astronomers trace the underlying distribution of matter, mapping how galaxies cluster together and form filaments. Amid these catalogs, the galaxy in question revealed its gravitational effect through the arcs of light wrapped around it. Follow-up observations confirmed the presence of the lensing arc and established its nearly complete horseshoe shape. This geometry is produced when the lens is massive and the alignment is close to perfect. The background source, lying billions of light-years farther away, is stretched and magnified, forming the bright arc visible in imaging data. Spectroscopy can then determine the red shift of both lens and source, providing distances and allowing astronomers to model the mass distribution of the lensing galaxy. With this information, the system became more than just an entry in a catalog. It became an important case study for the measurement of extreme galactic mass. The role of surveys in such discoveries cannot be overstated. Wide-field instruments like the Sloan Digital Sky Survey and its successors have provided maps of millions of galaxies, enabling statistical studies and rare finds alike. Gravitational lenses like the Horseshoe formed by this galaxy serve as natural telescopes magnifying distant galaxies that would otherwise remain unseen. They also provide a way to measure the mass of the lens itself without relying solely on the light it emits. In this case, the strength of the lensing revealed that the central galaxy contained far more mass than its starlight alone could account for. The arcs demanded an explanation rooted in gravity, not in luminous emission. The discovery phase also involved attention to detail. Identifying lensing arcs requires distinguishing them from other elongated features, such as tidal streams or coincidental alignments of galaxies. Careful inspection of color images and spectra confirmed that the arc light had a different red shift than the foreground galaxy, proving that it originated from a much more distant source. The curvature of the arc further supported the interpretation of lensing, as only gravitational deflection produces the symmetry seen. By excluding other possibilities, astronomers were left with the clear conclusion that this system acted as a gravitational lens of unusual power. Once confirmed, the system became a target for deeper imaging. High-resolution telescopes, both ground-based with adaptive optics and space-based without atmospheric distortion, refined the view of the arc. The clarity of these observations allowed detailed modeling of the mass distribution. Instead of a vague estimate, astronomers could reconstruct the profile of the lens, identifying how mass increased toward the center and how it extended outward into a broad halo. These models provided not just a number for the total mass, but also a map of how that mass was arranged. The results placed the galaxy among the most massive lenses known, with an inner core dense enough to suggest the presence of an extraordinary central black hole. Gravitational lensing discoveries are often celebrated for their visual appeal, with arcs and rings resembling shapes familiar to the human eye. Yet their scientific value lies in what they reveal about the otherwise invisible. Lenses expose dark matter. Halos confirm general relativity across cosmic distances and enable the study of galaxies too faint to observe directly. The case of the cosmic horseshoe created by LRG 3757 demonstrates each of these. It shows the strength of gravity in action, the reliability of Einstein's theory, and the scale of galactic mass that can be hidden beneath the glow of stars. The detection process also underscores the importance of alignment. The universe is filled with galaxies at many distances, yet only rarely do they line up so precisely that one can lend the other into such a dramatic shape. When such alignments occur, they are treasured opportunities. They allow scientists to probe both the lens and the source, simultaneously yielding information about two separate galaxies in one observation. The lens provides data on mass distribution, while the lensed source can be magnified enough to reveal details of its structure and star formation history. In this way, gravitational lensing is a dual probe useful for studying both the foreground and the background. In the broader scope of astrophysics, each new strong lens discovered expands the sample available for statistical study, with a larger set patterns emerge about how galaxies of different types and masses act as lenses. The particularly strong lensing produced by the galaxy in question adds to the high mass end of this distribution, helping to constrain models of galaxy formation and evolution. It shows that some galaxies, through mergers and accretion, can reach masses far beyond the norm, their gravity bending light into nearly complete rings. The recognition of this system as a lens and the subsequent modeling of its properties marked the beginning of a deeper investigation into its structure. What started as an entry in a survey catalog evolved into one of the most striking lensing examples in the sky. Each observation peeled back another layer, from identification to confirmation to detailed modeling. The result is not only a beautiful image, but also a profound insight into the nature of mass in the universe. Step by step, astronomers built the case that the system is among the heaviest galaxies ever observed, setting the stage for further exploration of its inner regions and the extraordinary concentration of matter at its center. When light from a distant galaxy passes near a massive object, its path curves, and the image seen from Earth becomes distorted. This effect, predicted by general relativity, is known as gravitational lensing. In the case of certain galaxies, the lensing is strong enough to create elongated arcs, multiple images, or even rings of light. Such structures are not artistic impressions, but genuine deflections produced by gravity. They allow astronomers to measure the total mass of the lensing galaxy with extraordinary precision because the geometry of the arcs is directly linked to the strength of the gravitational field. Among the known lenses, a few stand out for the clarity and completeness of their arcs. One of these is the system that creates a nearly circular horseshoe of light, a rare and vivid demonstration of the scale of cosmic gravity. The arcs encircling this system are formed by the light of a background galaxy located far beyond the lens. As the light travels for billions of years across expanding space, it encounters the gravitational field of the foreground galaxy. Instead of traveling straight, the photons follow curved paths wrapping around the lens and arriving at Earth as bent streams. Depending on the alignment, these paths can combine to form partial arcs or closed rings. In this case, the near-perfect alignment produces a striking arc that nearly completes a circle. The luminous curve contrasts against the dark of the sky, outlining the otherwise invisible field of gravity. Its symmetry provides a rare opportunity for measurement, since any departure from a perfect circle carries information about the distribution of mass within the lens. Detailed imaging of the horseshoe arc shows subtle variations in brightness and curvature. These variations are used in lensing models to reconstruct the profile of the lensing galaxy by adjusting parameters such as mass density, slope, and ellipticity. Astronomers reproduce the observed arc and thereby infer the actual structure of the mass distribution. This is not a guess, but a rigorous calculation constrained by the rules of general relativity and the observed data. The outcome shows that the central galaxy is immensely massive with its gravity bending light over a wide area. The arc does not merely surround the visible galaxy but extends outward, showing that dark matter plays a dominant role in shaping the field. The luminous horseshoe is thus both an aesthetic image and a map of invisible mass. The brightness of the lens dark is also valuable because gravitational lensing magnifies background sources. The distant galaxy appears brighter than it would without the lens. This allows astronomers to study its properties even though it lies billions of light-years away. In effect, the lensing galaxy acts as a natural telescope, amplifying the signal of a faint background source. This dual role makes lensing systems doubly important. They reveal the mass of the lens, and they provide access to the light of galaxies otherwise too distant to examine. In this way, a single observation yields insights into two epochs of cosmic history separated by billions of years. The horseshoe arc has become one of the most recognizable examples of strong gravitational lensing. Its geometry is used in educational materials to illustrate the principles of general relativity, while its detailed analysis provides data for professional research. What sets it apart is not only the completeness of the arc, but also the clarity of its symmetry. Many lensing systems show partial arcs or multiple images, but few produce such a nearly continuous curve. This rarity underscores the fortunate alignment of lens source and observer. It is a cosmic coincidence. And yet, within a universe of hundreds of billions of galaxies, such coincidences are inevitable somewhere. This particular one has offered an especially clear window into the mass distribution of the lensing galaxy. The role of lensing arcs in mapping dark matter is profound. Unlike visible matter, dark matter does not emit, absorb, or reflect light. Its existence is inferred entirely through its gravitational influence. Gravitational lensing is one of the few direct probes of this invisible component. By comparing the shape of arcs with the distribution of visible stars, astronomers can determine how much mass is dark and how much is luminous. In the case of the horseshoe, the mass required to produce the observed arc far exceeds the contribution of stars alone. The lensing signal therefore reveals an extended halo of dark matter surrounding the galaxy stretching far beyond the visible light. This finding is consistent with other studies of galaxies and clusters, but in this case, the clarity of the arc makes the conclusion particularly robust. The geometry of the arc also gives insight into the shape of the dark matter halo. If the halo were perfectly spherical, the arc would form a near-perfect circle. Deviations from circularity indicate elongation or asymmetry in the mass distribution. By fitting these details, astronomers reconstruct the three-dimensional shape of the halo. learning how dark matter is arranged on galactic scales. This information is critical for testing cosmological models, which predict not only the amount of dark matter, but also its clustering properties. The Horseshoe lens thus contributes to the broader effort of understanding the fundamental structure of the universe. Beyond dark matter, the arcs also shed light on the luminous content of the lensing galaxy. The stars in the central galaxy contribute to the overall mass profile, especially near the core. By combining lensing measurements with stellar population studies, astronomers separate the contributions of stars, gas, and dark matter. This multi-pronged approach refines estimates of the total mass and the relative proportions of its components. In the case of very massive galaxies, the stellar contribution becomes small compared to the dark matter halo and the central black hole. The Horseshoe arc points clearly to this outcome. The galaxy is dominated by unseen matter, with stars only providing a fraction of the mass needed to explain the deflection. The arcs are more than a scientific tool. They are a reminder of the scale of cosmic distances. The light forming the Horseshoe left its source when the universe was much younger, perhaps less than half its current age. During that time, it crossed expanding space, was bent by a foreground galaxy, and then continued to Earth. By the time it reached telescopes, billions of years had passed. What is seen in the arc is therefore a record of two galaxies at different times, one closer, one farther, their relationship revealed by gravity alone. This blending of time and space is a hallmark of astronomy where every observation is a look back across epochs. In studying the Horseshoe arc, astronomers have not only confirmed the immense mass of the lensing galaxy, but also strengthened the evidence for the presence of one of the heaviest black holes ever measured. The arc, while only a feature of distorted background light, is a gateway to understanding the unseen. Its presence confirms the galaxy's mass. Its shape refines models of dark matter, and its brightness allows the study of a background system. From the outer arcs of light, the path now moves inward toward the host galaxy itself, where the concentration of mass becomes even more apparent. At the heart of every gravitational lens is the lensing object itself, the galaxy, whose mass bends light and shapes arcs into the sky. In the case of the system producing the Horseshoe arc, the central galaxy is a luminous elliptical massive enough to dominate its surroundings. Elliptical galaxies differ markedly from spirals. They lack the grand arms of star formation, the disks of cold gas, and the prominent dust lanes that give spirals their layered appearance. Instead, ellipticals are smooth and rounded, their light distributed more evenly with stars moving in many directions rather than ordered rotation. Their populations are old, made up largely of low-mass, long-lived stars that have burned steadily for billions of years. The absence of cold gas means that new stars form only rarely, and the overall color of the galaxy is reddish, the hallmark of an ancient stellar assembly. The host of the cosmic Horseshoe is a giant elliptical galaxy, one of the largest kinds known. Such galaxies are typically found in dense environments, often at the centers of groups or clusters, where they have grown through repeated mergers. Each merger brings in more stars and sometimes funnels gas to the center where it can feed a central black hole. Over billions of years, this process builds galaxies with masses far greater than those of typical spirals. Their stellar halos extend far into space, their density dropping gradually outward, blending into the dark matter halo that envelops them. The galaxy producing the lensing arcs follows this pattern with a visible light distribution that matches models of mass.